Good morning, students. Today we are going to discuss the next unit, Unit 8, Relativistic Wave Equation. In some other book, you may find Relativistic Quantum Mechanics. In some other book, we can find this title as Relativistic Wave Equations. So, a lot of relativistic wave equations will be there in Relativist Quantum Mechanics. Okay, especially we are going to deal with two major equations as relativistic wave equations. One is a Klein equation, another one is Dirac equation, which both represent the relativistic quantum mechanics, relativistic wave equations, which are very, very important equations. And in this unit, we are going to discuss these titles: Klein equation, charge and current densities, which we are going to discuss today, and Dirac matrices, Dirac equation. As I said, these two equations are very important equation in relativistic quantum mechanics. Dirac equation, then plane wave solutions, interpretation of negative energy states, antiparticles, spin of electron, and the magnetic moment of an electron due to spin. So these are titles that we are going to discuss in this unit. So about relativistic quantum mechanics, we have been dealing so far about non-relativistic equation, and of course this equation is a non-relativistic equation which was proposed by Schrödinger. So we know about very well. This is just the extension of a non-relativistic equation when the motion of the particle approaches the velocity of light. So only then people will use this relativistic equation. And of course we know about this equation very well. This equation doesn't include spin, the first point. This equation doesn't include spin, whereas the Pauli's matrices can be added with the spin, added with the equation, extra. This is called extra fitting. So with this equation, we can add the Pauli's spin matrices with this equation. But this cannot be considered as a relativistic equation. Okay. Then another very important thing is, this is a second order differential equation, whereas this one is a first order differential equation in time. So look at this equation. This is a partial d squared psi by dx squared. So second order differential equation in space coordinates. First order differential equation in time coordinate. Space and time will not have any symmetry. Okay, this is inconsistent with the special theory of relativity. So 1900s, especially 3 decades in 1900s, 1910, 1920 and 1930s, two theories were developed. So one is special theory of relativity by individual Albert Einstein. Then another theory, quantum mechanics, was developed by many scientists. And in the year 1919, special theory was proved by Arthur Eddington from UK. So still Einstein became very famous. So people thought that every theory should be interpreted in terms of special theory of relativity. In special theory of relativity, space and time are symmetry. They are in symmetry. That means both will have same orders. Here we have second order and that is first order. Suppose the equation is same order, like for example Maxwell's equation. In Maxwell's equation, out of 4 Maxwell's equations, we have 2 Maxwell's equations will be in terms of differential operators. So those differential operators are in terms of first order differential operators. So they are space and time symmetry. So special theory of relativity goes with space and time or symmetry. So people started interpreting all the theories in terms of special theory of relativity because this was proved by Arthur Eddington in the year 1919. So similarly, Schrödinger himself, he wanted to interpret quantum mechanics, non-relativistic equation into special theory of relativity. So he wanted to prove this one. He wanted to interpret the results, whether it is consistent with the theory of relativity or not. This is one. Then another major idea is it must be invariant with Lorentz transformation. special theory of relativity, the physical laws and physical equations all are invariant in Lorentz transformation. So what we call this as covariance of Lorentz transformation. So they must be invariant. It must be same in all the frames of reference. Suppose we want to measure any physical equation, physical laws here somewhere, I will get some results. The same results also will be obtained in some other reference, some other place. So there must be some consistency should be there. Of course, in specialty of relativity, all the physical laws or equations, they are consistent in terms of Lorentz transformation. Okay. So similarly, they want to check whether it is consistent or not with the frames of reference, Lorentz frames of reference. So they want to check. So Schrödinger himself, he put forth, interpreted all the results from specialty of relativity into this one equation, and he could not find the results accordingly. It was not satisfied. He was not satisfied with the results, and results went wrong. And of course, he derived an equation. That equation was applicable for spin zero. Spin zero mainly for k mesons and pi mesons. So people said that this can be accepted only for the spinless particle. So he derived only, he himself attempted in the year 1926 the relativistic equation using the results of specialty of relativity, and he got the results. Those results are slightly modified. That is, this is applicable only for the spinless particles. That is spin equal to 0. So Klein and Gordon, which we are going to now see, Klein and Gordon, both the scientists independently they derived the equation, and the implications and applications of the relativistic equations was done by Klein and Gordon individually, and the applications were done. So that's why it is termed as Klein-Gordon equation. So as I said, Schrödinger himself he attempted to derive the first equation. He could not get the results properly because this is applicable only for the spinless particle. But we know that all electrons are spin particles. We know already. So, but the applications and implications are done mainly by Klein-Gordon. So that is termed as Klein-Gordon equation. Okay. So we are going to look today the Klein-Gordon equation and corresponding charge and current densities. Okay, this is about the probability densities which you have already seen earlier. Okay, so now we will go through the real text. So the first question is on Klein-Gordon equation. So Schrödinger developed the non-relativistic equation and also generalized the wave equation for a relativistic form. So he attempted. This equation has been taken from the transition in classical dimension from non-relativistic relation. As we know already about this E equal P squared by 2m, we know kinetic energy is given as P squared by 2m, we know already. And the corresponding relativistic relation between energy and momentum of the free particle is given by this equation. So this is taken from special theory of relativity. E squared equal to P squared C squared plus m squared C power 4. This is from non-relativistic equation. This is from relativistic equation. Okay. Now corresponding operators, and we know the operator for energy will be IH cross d by dt, partial d by dt, and the momentum will be minus IH cross del. And of course we know the equation E squared. So on both sides squared is there. So we are going to square the operators, corresponding operators. We are going to keep all the squaring operators into this equation. So for that we need to have the square of the operators. So V squared is given as, just to square it, it will give you minus h bar square d squared psi by dt squared, and this will become P squared equal to minus h bar square del square psi. We substitute in this equation, so which we have already seen, see earlier. So substitute in this equation. So now this equation becomes, you have minus h bar square d squared psi by dt squared r comma t, which is equal to c squared. Your c squared is here. Okay, your p squared will be minus h bar square del squared psi. So you have minus h bar square del squared psi of r comma t plus m squared c power 4 psi of r comma t. Look at this equation. Psi depends on r comma t. There is no spin at all. Suppose there is a term spin or spin 1 or otherwise velocity. Psi does not contain any spin 1. Psi does not contain any. One is spin, another one is velocity. It contains only the position. Suppose if it contains spin and if it contains velocity, then we can say that equation is nothing but a relativistic equation. So in non-relativistic equation, psi contains only r comma t alone. Okay. So now look at this equation. We have a second order differential equation in time. Look at this right hand side. Second order differential equation in space coordinate. See. So space time are invariant in under Lorentz transformation. Both orders are the same. In Schrodinger equation, look at the Schrodinger equation, orders are different. Second order differential equation. This is first order differential equation in time. Whereas here, look at this equation, both orders are equal now. So we can say that space and time are invariant under Lorentz transformation. They are symmetry. Okay, so this is what Schrodinger himself attempted. So now you bring this term to left hand side. So you bring this term to left hand side, you will have this term. Okay, as I said, space and time are invariant under Lorentz transformation. You just divide by h bar squared c square. This equation you divide by h bar squared c square will give you del squared psi r comma t minus, you are going to divide. Okay, this h bar squared will cancel. We have minus 1 by c squared d squared psi by dt squared, which is equal to m squared c squared c to the power 4 divided by 1 c squared is there. So that will get cancelled. You have m squared c squared divided by h bar squared psi. Is it okay? I can pull this psi out and get the equation 8.8. Is it okay? So you have del square minus 1 by c square d squared by dt squared together in a bracket. Then we have remaining term will be psi, which is equal to m squared c squared divided by h bar square. And put together we call this as square del square. This is called square del square. Okay, square del. Okay, this is ordinary del. We know Laplacian operator. We know del square. This is square del. So square del square. So this is known as square del square. So square del square psi, which is equal to, and we are talking about suppose if m naught is as rest mass energy, m is the particle moves with velocity, some other velocity. Okay, then we can say that m. So this is m naught c square divided by h bar square psi, and we call this operator as D'Alembert operator. Okay, D'Alembert operator. Is it okay? So del square is given as this term. So this equation is known as Klein Gordon equation, which is space-time invariant under Lorentz transformation, because both orders are the same. Here also you have second order differential equation in space, second order differential equation in time. So orders are the same. So that's why it is termed as space-time are invariant. However, there is no spin. So this equation is applicable only for spin is 0. Okay, there is no spin contribution here. Of course, this can be used for k meson and pi meson where spin is 0. For the particles, spin is 0. Okay, so this is known as Klein Gordon equation. It is invariant in space under Lorentz transformation. So your del squared is termed as, we know that already, del squared can be written as this term, partial d squared by dx squared plus d squared by dy squared plus d squared by dz squared. This term can be written as d squared divided by partial d ICT whole square. So this is for 4-dimensional space. This is first one, second one and third one, and the last one is time coordinate. What we call this x to the power 4, which is equal to ICT. We call this as Minkowski space, probably which you have studied in UG third year, okay, undergraduate third year, about Minkowski space, 4-dimensional space. So this is termed as. So equation 8.5 has a plane wave solution of the form. So just assume that the solution of this equation is a plane wave solution, e power ikr minus omega t. you just differentiate with respect to r, with respect to t 2 times. Okay, when you are going to differentiate this with respect to r, will give you ik e power ik dot r omega t. Correct? We are going to differentiate with respect to r. So this becomes ik e power ik dot r minus omega t. Again you differentiate, that will give you ik multiplied by ik. So ia will give you I squared minus 1, so that will be minus k squared e power ikr minus omega t. Okay. Differentiate with respect to time. So that will give you minus I omega e power ik dot r minus omega t. So you are going to differentiate again. So that will give you as minus I omega multiplied by minus I omega, minus minus plus I into I squared minus 1. So that will give you minus omega squared e power ikr minus omega t. Is it okay? So you will have to differentiate 2 times with respect to r and t and substitute here. Okay. So substituting equation 8.12 and 8.13 in equation 8.5, we are going to substitute. We will have exactly, after substitution we will have equation 8.14. Okay. Just take the common terms out, cancel the common terms. When you are cancelling the common terms out, that will give you h bar squared omega squared, which is equal to h bar squared c squared k squared, you have m squared c power 4. Okay. So now just take the root, taking the root on both sides. So you have h bar omega, taking the root, that will give you plus or minus h bar squared c squared k squared plus m squared c power 4 to the power 1 by 4, taking the root. Okay. So we know that eigenvalue of energy E equals nothing but h bar omega. Eigenvalue of the energy is given as h bar omega. So your E will be plus or minus h bar squared c squared k squared plus m squared c power 4 to the power 1 by 2. Okay, to the power 1 by 2. Now look at this term, it is given as plus or minus. Look at the term, it is given as plus or minus. That means the energy can be positive as well energy can be negative. But there exists no negative energy in physics. All the energies are positive. So far we have learned only energies are positive. No energies are negative. But negative energy is meaningless. See, Schrodinger himself also obtained the same equation, same result, and Klein also they obtained the same results with a negative energy. Mathematics is correct. Look at the mathematics. The derivation was very nice. Look at the derivation, mathematics, everything was correct. But what about physics? So physics went wrong or somewhere went wrong somewhere? We do not know. That negative energy was interpreted by Dirac after 2 years. So this was done, Schrodinger done in the year 1926, and Dirac also attempted same thing in terms of a different Hamiltonian, what we call this a Dirac equation. He also attempted. He also got the same negative energy in the year 1927. Then he could exactly interpret the results of negative energy states in the year 1930. So which we are going to see. Okay, so the positive and negative square roots in equation 8.15 correspond to the conclusion the sign of energy. Mass is correct. Okay, so we have to interpret exactly the negative energy. It implies that the energy of the particle can be positive as well as negative. The free particle in relativistic quantum mechanics will have positive and negative energy values. However, at first we are going to take only positive energies only we are going to take. Dirac in the year 1930, he interpreted the negative energy states in a clever way after 2 or 3 years. He also obtained the negative energy values, but he interpreted exactly the negative energy states in a beautiful way. All the electrons in a vacuum state, they will be in one level. Okay, they will be in one level. Suppose if there is any perturbation, any external perturbation occurs, and these electrons will be liberated and they will go to the different levels. When they are going to the different levels, they leave the small hole. So after electron goes to the higher level, it will leave small hole. This hole is called a Dirac hole. Okay, this hole is called a Dirac hole. After leaving, this hole will acquire exactly the opposite property of the electron. For example, electron has, of course, we know spin, charge, we know, and mass. Just now I said opposite property. Those properties except the sign. For example, this is electron is referred as minus E. I am going to refer this antiparticle as plus E. Sign alone will change. Mass will be same. Spin will be same. Okay, charge will be the same except the sign. That is minus E, here it is plus E. So Dirac hole is considered as an antiparticle. So negative energy states. So it exists in the negative energy states, all the particles. So this is what he differentiated. So negative energy states exist. And after 2 years, 1932, Anderson from US, he invented these positron antiparticles in the experiment of cosmic rays in the presence of magnetic field. So in 1932. So in 1930, Dirac proposed the antiparticle, whereas in 1932, Anderson discovered the antiparticles in the experiment of cosmic rays in the presence of magnetic field, for which Anderson got Nobel Prize in the year 1936. Dirac got the Nobel Prize in the year 1933. He shared the Nobel Prize with Schrödinger. In fact, in 1932, Werner Heisenberg got the Nobel Prize. So people announced, Nobel group, they announced the Nobel Prize for Werner Heisenberg in 1932. And he got the Nobel Prize in 1933. So in 1933, 3 persons got the Nobel Prize. So Werner Heisenberg, Paul Dirac, and Schrödinger. So that's the beauty of physics. So we have negative energy states exist. Okay. So that's why we call Dirac as father of antiparticles. Okay.